EX124. Let's come back to homological algebra, talk about abelian categories. So let me recall some type of categories. Firstly, what we call AB category, not yet abelian. So category A is called an AB category. If every home set in A is abelian group, in general it's just a set, but here is abelian group. Sometimes this is called what is this called? Z category, I guess. Yeah. It's not yet finished, such that the composition law distributes over addition of this abelian group. Let me put a remark. In particular, let's say if you take objects in this category A, let's take objects A, B, C, D. Let me put F, J, H. Then the composition law will tell you that F there exists such a map, and we require distribute over addition. This will tell you that this is the same as this. Secondly, let's remark that in particular, if we take all the rings, all the objects to be the same, let's still use the notation of J. So what do we have? This is telling you that, so over this abelian group, this is abelian group, over this abelian group, if you take elements of it, we can define multiplication by composition, or reverse the order maybe. And after we define this axiom of distributivity tell you that actually there is associative and it's compatible with addition, and so this have a ring structure. Yeah, in particular we have the identity here, so the identity multiply with whatever f is f itself. This comes from the associativity law, right? And fg prime equals fg prime, something like that. And then this is a ring, and conversely you could put a ring structure on this home set, right? Kind of equivalent to this is the home set is nothing but a ring. Any ring could give any ring, you could put this ring structure on a home set of AA, Conversely, any home set is always a ring. Secondly, additive category. So this is smaller and smaller subcategory of AB, containing AB category. So firstly, it is an AB category. Let me write it very simply. With a zero object, with a product for any pair A and B, from this category. Remark. This would imply that finite product, this additive category, finite product exists and is the same as finite coproduct, which means finite coproduct exists also. Traditionally, finite product is written as when it's finite, then this is the same thing. And then abelian category. It's firstly an additive category. So this is again contain the additive category, contain the AB category. Firstly, additive category such that some axioms. Firstly, let's call it AB1, following Webber's book. Every map A has a kernel and co-kernel. AB2, every monic in A is the kernel of its co-kernel. So monic is always kernel of co-kernel. Kernel and co-kernel exists. Lastly, every epimorphism is the co-kernel of its kernel. So 3 and 2 are kind of due to each other. Remark. This is telling that abelian category monic is the same as kernel. And epimorphism the same as co-kernel. So always keep in mind all those good properties are satisfied by the category of our modules. Yeah, exercise 1. So this is very easy. Let's just talk about it very quickly. Let A be category and given morphism from object B to C. Then first claim, this F is monic if and only if for every non-zero Fe is non-zero. Secondly, F is epimorphism if and only if for every non-zero G of F is non-zero. So you just change the position, reverse the position of F with arbitrary map. So the proof is easy. So recall that F is monic. Let's just take the first one as an example. If and only if by definition, if you have A to B, and then F B to C, for any E1, E2, FE1 equals FE2 implies E1 equals E2. Right, and this is equivalent to say that under the same condition, FE1 minus E2 equals 0 implies E1 minus E2 equals 0. Right, so we can do this addition, subtraction, multiplication. Multiplication comes from the composition law, and this addition, subtraction comes from the abelian structure of the home set, because this is AB category. Obviously, this is equivalent to saying that F E equals 0 implies E equals 0, or E doesn't equal 0 implies FE doesn't equal 0. You could do the cancellation from left hand side. Well, the surjective tells you could do the cancellation from the right hand side. Some sense. Is it correct to say like this? Remark. Let me check. Question. F is epimorphism. Firstly, does it imply that F what do I want to ask? Cancellation from left hand side. Yeah, that's exactly. Right, that's the cancellation from left hand side. And sorry, this is an inject monomorphism, and epimorphism implies cancellation from right hand side. Right, this is exactly the same. My remark is to summarize this as a slogan. So mono is the same as cancellation from left hand side, cancellation from right hand side. And then for abelian category, let me put a remark. We have proved that if A is abelian, then A op is abelian. This is exercise we have done before, maybe 30s, around 30s, 20s, I'm not sure. We've also proved that for any category I and A abelian, so I we don't require to be abelian, any category and A abelian, then the functor category is abelian. And then let's further discuss extremes, three and four. Following Weber's book, so AB3 is said that for every set AI for objects of A, the coproduct exists. And the coproduct is often called direct sum. It is often written direct sum. And we see that A is cocomplete if it satisfies AB3. Correspondingly, there is complete, as you could imagine, Let's call this AB3 star. It's talking about product for every set. Objects in A. The product exists. In A. Rather than saying it satisfies AB3 star, we'll say that is complete. Again, this abelian groups, the category abelian groups and that category of R mode both satisfy this. They're both complete and co-complete. But so the finite abelian groups form an abelian category. Finite abelian groups form an abelian category, but this is not complete, neither co-complete. Now let's do our second exercise. Talk about union and intersection. Let AI be a family of subobjects of object A show that if A is co-complete, then there is the smallest subobject it's denoted by the summation AI, subobject of A containing all AI. Conversely, if A is complete, then there is this largest subobject denote the intersection of AI. We contained in all AI. Let's prove this. So the idea is that I might think of, for example, co-complete. By definition, it means that there exists coproduct. So we would take coproduct. And then subobject means there is a monic map. And then by the universal property of coproduct, this is telling you that there exists some map F such that this is commute for any I. But this doesn't force this F to be injective. It's only telling you this is injective, but this is not injective, but we'll claim that there exists the smallest object of AI, smallest object containing all of those sub-object AI, and it is itself a sub-object of A. So what we do is we use the fact that this is an abelian category, and so yeah, let me first mention, I forgot to say, for an abelian category, we have further conditions, AB3 star, okay? So this is abelian category. So for abelian category, we have this unique factorization as surjective, injective, AP mono, image F, co-image of F, and this is a good candidate to be a sub-object of A. So let's write it more precisely. Let's first have this AI. And then let me test for any subobject of A contains AI. We want to prove that this image of F is contained in B, and so this is the smallest object, sub-object of A containing all the AI, right? Then why? Because firstly, let's say by the universal property we have this map making the diagram commutes. Here you have commuting diagram. And all of this making the diagram commutes. And so this square commutes, and this smaller square commutes. This is telling you that this is the same as this, and so the question is I'm asking, is this commutative? So let's first say if this is commutative, then what I'm going to do is I'm going to write this as, so this is both image and co-image. I'm going to write this as the co-kernel of kernel F. I write this kernel F. And then notice this compose this is 0, this compose this is 0 if it's commutative, and then this is injective, this is handling that this, compose this is 0. And so by the universal property of cokernel, forces this to factorize. But then this is injective, I mean this is injective and making diagram commutes to force this to be injective. And so this is contained in P and we are done. How do I see this? Question mark is commutative. The problem is that, let me call this I. I have F compose I equals, let's call this composition G. But this does not in general tell you F equals G, as we see. Monomorphism tells you to cancel from the left. But imagine if we're working with modules, then this is okay. Because this works for all those I. It is surjective onto each factor of it. So let me left this as a sub-exercise. And then now let's look at the due of this question. This is a thing that can I have a biggest, so this is like the smallest union of all those sub-objects. Now we're looking at the biggest intersection. So the setting is let's write this. Sorry, reverse the direction. Maybe let me write this. We have this map for any other object contained in all the AI. We want to show that this is the smallest containing all the AI. Suppose B is another object containing all those AI, then by the universal property of product we have this map. And then again, this is not yet a sub-object of AI. We'll factorize through it. Let me put this time kernel of the co-kernel. And then again, we want to show that we want to show the smallest, so we want to show that the largest. We want to show that there is such a map from B and it's injective. How do we see that? So again, by universal property of kernel. So this composed with this is the same as this, and so in particular is 0. So we have this. And once you have this, then the commutative of this diagram tell you that this must be injective, and so we are done. Very strangely, we don't have the similar problem as we have in this version. To determine commutative of this diagram. What is a diagram? Yeah, actually, to check the commutative of this diagram, you could. It's the same as checking the commutative of this diagram and this. Yeah. Anyway, let me left this as some exercise.